Hey everyone, welcome to our video lesson on the recursive formula. This goes with our sequences that we've been doing for the past couple of weeks, but this is just a different way to represent those sequences that we've been learning about. So go ahead and grab your notebook, something to write with. You might want your calculator, but I don't think it's necessarily going to be required for today. All right, so right away into definitions. What is the recursive formula? Well, the recursive formula, like I said, is a different way to represent the sequences we've been learning about. Whereas last week we talked about the explicit formulas of arithmetic and geometric sequences specifically, recursive formula is just a way of representing a sequence by describing each term as a function of the term before it. So we were actually talking about sequences recursively when we first got introduced to the pattern that a sequence might have. For example, if I take a number and then I add 3 to get the next number and then add 3 to that to get the next number and so on and so forth, that's actually looking at the sequence in a recursive manner. What I'm going to show you guys today is how we mathematically write the recursive formula and how you're going to read it so that you can show what the sequence is that they're talking about. There are two requirements for a recursive formula. You need to always tell the reader where the sequence starts and how to get to the next term. Okay, because if I sat here and I said, oh, I'm thinking of a sequence where every term is the number before it multiplied by 5. We could all sit here and think of different sequences that have that pattern to it. The difference being maybe I start at the number 1 and then continue to multiply by 5, whereas someone else may start at the number 7 and continue that multiplying by 5. So it's really important to write where the sequence starts and how you get to the next term. And it's this built up pattern that the recursive formula kind of depends on. So when you see recursive, think of it like climbing a ladder. In order to get to the top, you have to take each step getting up there, and that's what a recursive formula does. It shows you the first step, where your sequence starts, and then it shows you how to progressively step to the next term, and so on and so forth. All right, so I'm going to go through a couple of examples written what I like to call informally. So this is the very basic way to kind of describe a recursive formula. And my first two examples, you'll notice they're both number 1. I'm going to do the one on the left. You're going to do the one on the right. But both of these sequences are arithmetic. Okay, this one has a common difference of 7. As I move from one term to the next, I add 7 every single time. So if I want to describe this sequence recursively, what I would have to do using the two required pieces is tell you what the first term is. So I might say the first term is 10. And then I would tell you how to get the next term according to the term you have now. So this is almost like an English statement about a mathematical sequence. The next term is the term you're at now plus 7. Okay, so if I'm standing at the 24, the next term that I want is this term plus 7, and that's how I got 31. So if you want to pause the video now and try another arithmetic sequence, see if you can come up with the recursive formula. The next two are geometric sequences. Okay, similar here, I'm going to start by telling you what the first number or the first term of my sequence is. So I'm going to start by saying the first equals 9. Okay, but now the pattern here, as I move from one term to the next, is multiplying by 2. So if I want to define my next term, I'm going to say the next one is 2 times the term I'm at now. Okay, sometimes you'll write that now in parentheses to show multiplication. I put a little dot there, and then sometimes there is nothing that shows up. Remember, a number next to a variable, which this word now is just a variable, a number next to a variable means multiplication. Again, this one on the right-hand side, also geometric, so maybe take a second and see if you can write the recursive formula for this sequence. The beautiful thing about recursive formulas, and the reason that we introduced this to you guys in 9th grade, is because you can use this process for sequences that may not fit into the arithmetic or geometric bubbles. Unfortunately, we only have explicit formulas, which we learned about last week, for these two patterns. But if I gave you guys something that looked like question number 3 down here, There is no common difference. I'm not adding the number every single time, and there is no common ratio because I'm not multiplying by the same number every single time. So I wouldn't be able to write an explicit formula for the sequence. I wouldn't be able to write something that would give me any term in the sequence that I was looking for. So this is where recursive formulas are actually very helpful. Remember, there's two pieces. I have to tell you what the first term is, so where to start. First one is equal to 1. And then I have to tell you what the next term equals. Okay, now this sequence does have a pattern. I said it didn't have a common difference and it didn't have a common ratio, but it does have a pattern. And you might take a little time and trial and error and guess and check, but the pattern here is to multiply by 3 and then add 2. Multiply 5 by 3 and you get 15, add 2 to that and you get 17. Multiply 17 times 3 and you get 51. Add 2 to that and you get 53. So if I want to define the next number that I'm looking at, let's say I want to fill in these ... dots, I need to take the term I'm at now, multiply it by 3, and add 2. And that would look like this. 3 times the term you're at now plus 2. So take a second, if you haven't already, pause the video and see if you can come up with the 3 recursive formulas for the 3 sequences on the right. All right, so how'd you guys do? The first sequence, arithmetic, was a common difference of -2, so -2. The next one had a common ratio of 10, so multiply now times 10. And then the last one was a challenging pattern. It required you to take half of the term you're at now and then add 2 back to it. So half of 20 is 10, 10 plus 2 is 12. Half of 12 is 6, 6 plus 2 is 8, and so on. Okay. Now, unfortunately, mathematicians don't generally use words like next and now. Even the term first is too much. The beautiful thing about mathematics is it's the same across every language, and not every country uses words like first, next, and now. So we have mathematical terms to represent words. You guys know that first is going to be represented by a sub 1, so I'm not going to go through that here. But the term that we're at now, if you're ever talking about the current term or the current spot in the sequence, that's what we're going to use our a sub n, or we also learned about it in function notation as f of n. Okay? That's how we're going to represent the word or the term now. The next term that would come right after it in the sequence, if this is the third term, the next term would be the fourth term. If this one's the fourth term, the next one would be the fifth term. Anytime you want to get to the next term, you just add 1 to that spot. So if I know that now is a sub n, the next term is a sub n plus 1. And that whole expression n plus 1 is in the bottom right-hand corner, subscript notation. Similar in function notation, the next term is going to be represented by n plus 1, because I'm just talking about one more spot over in the sequence. Okay? It's not used as frequently, but the previous term is going to be this spot minus 1. You're taking it back 1, so this would be a sub n minus 1. And in function notation, again, we would just take that n minus 1 and put it in the parentheses. Okay, so I'm going to use this notation down here instead of the previous now and next in order to write the recursive formulas for these 4 examples down here on the bottom. And the beautiful thing about your recursive formula, unless it's specified in the question, is you can choose. All right, you can choose if you're going to write it in sequence notation or function notation. And you can choose which 2 terms you're going to relate to one another. Okay, now in all our informal examples up here, I always used next and compared it to what I'm at now. So I would use a sub n minus 1 in this spot equals a sub n in my now spot. You can also compare what term you're looking at now according to the term that came right before it or the previous term. So sometimes you'll see a sub n equal to some version of a sub n minus 1. As long as you're taking 2 of these in a row, either comparing these 2 or these 2, then you are doing it correctly. All right, so let's take a look at some examples. This one, question number 1, I go from negative 70 to negative 60 to negative 50 and so on. And that is an arithmetic sequence. I'm starting at negative 70, so right away I'm going to satisfy my first requirement. A sub 1 equals negative 70, comma. And then my term I want next, I'm going to use the sequence notation. A sub n plus 1 is equal to the term I have now plus 10. There's my common difference. So the now is going to be a sub n plus 10. And notice how my plus 10 is up on that line. It's the same size as my equal sign and my A letter. I'm saving that corner subscript notation for just the spot in the sequence. Okay? Let's look at number 2, and this one I'm going to throw a curveball and write it in function notation. Always start with what your first term is. So in this one, f of 1 is equal to 3. That's how I'm going to start my recursive formula. And now I have to talk about how do you get to the next term in your sequence according to what you have right now. How would I fill in this spot? Okay. Well, upon investigation, you would notice that this sequence is a geometric sequence because going from 3 to negative 12 and then negative 12 to positive 48 has a pattern of multiplying by negative 4. So my term that I want next, which I'm going to use this notation, f of n plus 1, is equal to the term that I have now times negative 4. So I'm going to write that mathematically as negative 4 times f of n. Okay? Now, finishing up with these examples, I just want to show you guys how we can also compare the term you have now according to what you previously looked at. So this doesn't go as well with our informal examples up at the top, but as long as I'm comparing 2 of these in a row, we are doing the right thing. Okay, so let's take a look at number 3. 40 to 20 to 10 and so on. Again, I have a geometric sequence. What's the multiplication pattern here? Well, every single time I'm dividing by 2, which means I'm multiplying by 1/2. So I'm going to go back to sequence notation for this one. So we always start with a sub 1 equals. That's going to be the easiest part of every recursive formula you write. What is the first term? But now, instead of using a sub n plus 1 to talk about the next term that I want, I'm going to take a step back. The term that I'm at now, a sub n, is equal to the term I had before that, a sub n minus 1, multiplied by 1/2. So this would be 1/2 a sub n minus 1. Okay, and last but not least, the fourth one is another arithmetic sequence. It goes from 19 to 13 to 7, and if you investigate, you'll notice that every single time you are subtracting by 6. So I'm going to go ahead and use function notation just to keep it interesting, but I'm going to start with the first term. The first term is 19. The term that I want to look at right now, let's say that this is the term I want to know right now. I want to know what this one is. That now is f of n, and the term I want now is the term I had before it, minus 6. So it's f of n minus 1 outside, minus 6. So a lot of different ways to write this recursive sequence, and recursive formula, and I don't want you guys to feel overwhelmed. The beautiful thing is you have choice. So if you find it more comforting to use sequence notation instead of function notation or vice versa, great. If you want to stick to next equals now, or if you if it's clicking more easily to talk about now in terms of the previous, you do you. All right, but you'll see all of these types come up in our next few practice activities, and then I will also be testing you and making sure that you can at least understand what they're saying if those come up. Last thing that we're going to do is actually use these formulas. All right, so what I have here is I have 3 sequences represented by their recursive formulas, and I covered up the second 2 so that we can all pay attention and focus on one thing at a time. Our job is to find the first 4 terms of each sequence. So I'm going to, right away, I'm going to set myself up with a little answer spot, right? I'm going to put those curly brackets to collect my whole sequence together. And what's great about the recursive formula is that it always tells you where the sequence starts. So a sub 1 is 100, which means I already have one of my terms given to me in the formula. Right, now, breaking down this second piece is what's going to be the tricky part for a lot of people. Remember, a sub n means the term you have now, or you want now in this case, and a sub n minus 1 is the term you want next, minus, oh, I'm sorry, that's not next. I'm thinking n plus 1, previous. And then it's minus 10. Let's bring this all down to one row so that we are not confused. So we've got a sub n, which is the term I want now. A sub n minus 1 is the term I was at previously, and then I'm going to subtract 10. Okay, so if I want to know the second term of the sequence, I'm going to take the previous term, or the one right before it, and subtract 10. Well, that's 90. If I then want the third term of the sequence, I'm going to take the term that was right before it, the previous one, and subtract 10. That's 80. And then the fourth term would be the previous term right before it, subtract 10, 70. And they only asked me to write out the first 4, but I could continue with that pattern as far as I needed to. Take whatever term you want right now, find the term before it, and then subtract 10. So let's look at another example, and hopefully I don't write the wrong thing down again. All right, I'm going to set myself up with a little answer box. Here's your sequence in recursive form. The first term is 7. Awesome. There's one of the terms that I have to write. And this says the term that you want now is 3 times the term you had before. So again, this represents now. F of n minus 1, take the whole thing out, that's previous. And they're just saying it's now equals 3 times previous. So let's write out the first 4. If I want this term now, take 3 times the one before it, that's 21. If I want this term now, take the one right before it, 3 times that would be 63. And if I want this term now, take 3 times the previous one, which would be 189. And those are the first 4 terms. Last but not least, and the reason that we introduce recursive formulas, here is a sequence represented recursively that doesn't fall into that arithmetic or geometric pattern. Okay, now again, it tells me what a sub 1 is, so I can already get a head start on my answer. But now, not only am I using a sub n plus 1, just means the next term, and a sub n, which means the term now, okay, but my pattern is a little bit more complicated than just subtract 10 or multiply by 3. If I want the next term, I'm going to take half of what I have now and then add 1. You'll notice that plus 1 is big. It's the same size as the 1/2 in the A. It's not in the subset corner notation part of it. All right, so what I'm going to do if I want the next term, which I do, I want the one that comes after 18, I'm going to take half of what I have now and then add 1. So what's half of 18? That's 9. Add 1, you get 10. Okay, if I'm there at the 10, the next term is half of where I'm at now plus 1. So what's half of 10? 5 plus 1 is 6. And now I'm at the 6. The next term is half of where I'm at now plus 1. What's half of 6? 3 plus 1, 4. And so on and so forth. Okay, so this would be helpful if they asked a question like, find the 5th term of the sequence. Unfortunately, that means you're going to have to write out the 1st, 2nd, 3rd, 4th to get to the fifth. But a lot of times they'll ask you for something very close to the beginning, like the third term or the fourth term. They won't ask you anything obnoxious like the 75th term. All right, so if you have any questions on recursive formulas, come to the Zoom Extra Help or shoot me an email to ask your question, because tomorrow you are going to be responsible for some practice problems. Have a great day, everyone.